Hello ladies and gentlemen, welcome to this video lesson on finding partial and total pressure using Boyles and Charles' laws. Why are we having this departure from our normal content, Algebra 2, Pre-Calculus and Calculus? Well, it's because one of our calculus students, Kinsey, has a chemistry class, and as a calculus class project we helped her out a little bit with this class, and this problem here is this one here. At 5 degrees Celsius, a 1 liter flask contains 3 times 10 to the negative 2 moles of nitrogen, 3 times 10 to the 2 power, which is 300 milligrams of oxygen, and 3.3 times 10 to the 21st power molecules of NH3, which is ammonia. What is the partial pressure of each gas, and what is the total pressure in the flask? And so for this, we're going to use a formula, which is this one right here, PV equals nRT. And this formula is the form of the combination of Boyle's law and Charles' law. And Boyle's law deals with the proportionality of pressure, and Charles' law has to do with how temperature and volume are related. And so the combination is this formula right here. And we're going to solve for, we're trying to find pressure. To solve for pressure, our pressure is going to be equal to nRT over the volume. And let's go find what some of these constants are. First of all, we're dealing with 5 degrees Celsius. Now 5 degrees Celsius, we have to put this in terms of relative to absolute zero, which is degrees Kelvin. So we have to add 273 degrees to that 5 degrees and get, for our temperature, we're going to be dealing with 278 degrees Kelvin. And then as far as our R, it's going to be our universal gas constant. Well, that's going to be 0.08206, and our units for that are going to be in liters an atmosphere over degrees Kelvin moles. And these things are going to cancel out here. Now let's go find the amount. Now it seems like the purpose of this exercise is to demonstrate that the elements in a sample of gas can be measured in different ways, in moles and in milligrams and in numbers of molecules. And so we're going to go to moles for using this formula, and to do that we're given already that our N value of our nitrogen is equal to 3 times 10 to the negative 2 moles. I'm just going to put moles like sometimes you'll see it as MOL, MOLE, MOLES. I'm going to put in moles. And our amount of our oxygen, we're given a starting value of 3 times 10 to the 2 power, which is 300 milligrams. That's milligrams of O2. And what we're going to do is we're going to convert that to grams by using dimensional analysis and multiplying by 1 gram per 1,000 milligrams of O2, and then we're going to multiply that by our 1 mole of oxygen per our atomic weight, which is going to be 32 grams of O2. And so we're going to have cancellations all around here. So milligrams, cancel milligrams, grams, cancels grams here, and then what we have left in the numerator is moles of O2. And let's go to the calculator. We're going to, in our calculator, we're going to have 300, which is our 3 times 10 to the 2 power over 1,000 times our molecular weight, which is 32, and for that we get 3 over 320. I'm going to try to put this in decimal form. I'm going to go to math, decimal, and we get this right here. It's going to be 9.375 times 10 to the negative 3 power. So now we are in moles as far as O2. Now for the number of moles of our ammonia, we're going to start out with numbers of molecules. So we're going to have 3.3 times 10 to the 21st power. That's going to be our molecules. Of our NH3, and that's going to be, we're going to multiply that by, we have 1 mole of NH3 per this number right here, 6.022 times 10 to the 23 power molecules of NH3. This happens to be something known as Avogadro's number, the number of molecules in a mole. So we can just go ahead and put this in our calculator and get this amount. So we start out with 3.3 times 10 to the 21st power, and we're simply going to divide that by Avogadro's number, 6.022 times 10 to the power of 23, and for that we get this right here. We get approximately 5.480 times 10 to the negative 3 power and that's going to be moles. That's going to be a lot of moles. I think this is going to be tough to breathe and survive at all. So what we're going to do is we can get the total number of moles, and that's going to be what we have to work with in getting our pressure. So if we add all these up together, we're going to have our number of moles are going to be this right here plus 0.009375 plus we have 3 times 10 to the negative 2 power. And so this is going to be our total number of moles here, which is going to be 4.4855 times 10 to the negative 2 power. So 4.4855 times 10 to the negative 2 power moles. That's total moles. So next thing we're going to do is find our total pressure. And our total pressure we're going to get by taking all these together, and that's going to be this one right here, nRT over V. So total pressure is going to be equal to 4.4855 times 10 to the negative 2 power. And that's going to be moles. I'm just not going to write down units so much here. Times our universal gas constant, which is 0.08206. And then it's going to be times 278. And it's going to be all over 1 liter, because that's our V, 1 liter all over 1. And so just putting that in the calculator, we have 4.4855 times 10 to the negative 2 power. And we're going to multiply that by our universal gas constant, 0.08206, and times our value of T, which is our temperature, 278 degrees Kelvin, and we're going to divide that by 1. Well, I'll just put 1 down here. So this is our pressure right here, which is going to be in atmospheres. So it's going to be around the nearest 4 decimal places, 1.0233. So 1.0233, that's going to be atmospheres. So that's going to be a big part of our answer right there. And then we're going to now go to a partial pressure. And for a partial pressure, we're going to look for proportionality. So our pressure of our nitrogen is going to be what proportion it is of the whole. And so we're going to take our number of moles of nitrogen, which is 3 times 10 to the negative 2 power, over our total moles, which is 4.4855 times 10 to the negative 2 power, and that's going to be we can just take this 3, be 3 over 4 point. So you have 3 over 4.4855, and we need to multiply that by the number of the atmosphere total, so it's going to be 1.0233, and we get 0.684. Times 1.0233, and we get 0.684 atmospheres. And then our pressure of our oxygen it's just a proportionality thing. We're going to have in this case 9.375 times 10 to the negative 3 power over, again, 4.4855 times 10 to the negative 2 power. And again, we're going to multiply that by the number of atmospheres total. We have 1.0233. And for that partial pressure, we are going to get 9.375 times 10 to the power of -3 over 4.4855 times 10 to the -2 power, and multiply this by the total number of atmospheres, which we have 1.0233, and for this we get a partial pressure of 0.214 atmospheres, or 0.214 atmospheres. And then lastly, what we have is our partial pressure of ammonia is going to be equal to our amount of ammonia, which is 5.48 times 10 to the -3 power over, again, 4.4855 times 10 to the -2 power, and again we multiply that by our total atmospheric pressure, 1.0233, and so we go to our calculator again for the last time. We have 5.48 times 10 to the power of -3. Oops. It's not to the power of. Okay, times 10 to the power of -3 over 4.855 times 10 to the power of -2, and multiply that by our total atmospheric pressure of 1.0233, and we get 0.125 atmospheres. Which is going to be roughly 1/8 of the total atmosphere. So if 1/8 of your total atmosphere is ammonia, you're not going to live too long breathing that mix. And then as a last check, we can add these three together and see if we get our total atmosphere, just kind of a final arithmetic check. So we have that atmosphere there plus point. See, it gave me the ANS, which is just repeating this 0.125. Then we add the 0.214 for the partial pressure of oxygen, plus the 0.684 atmospheres of nitrogen. Yes, we get 1.023, not 233, but close to it. So these are going to be our answers here for our partial pressure of nitrogen, partial pressure due to oxygen, and due to ammonia. So I hope this has been helpful to you. Good luck, and thanks for viewing. And we do this because learning never ends. Take care.